Hello, we will continue with the Gatu variation today to establish the necessary conditions for the minimization of a functional. So, this lecture will reinforce some of the concepts we discussed in the last lecture, that is the Gatu variation and variational derivative, Frechet differential and Frechet derivative, but the focus will be on the Gatu variation. Okay. So, let us start with a functional. Okay. So, let us take a problem. Let us say I want to minimize a functional j, which we take it in the form of an integral now going from x1 to x2, integrand f which depends on a function y and y prime, and if you want we can also put y double prime as well and dx. Okay. And we are minimizing with respect to this function y of x, which we need to find to minimize this. So, what this means is that this implies that we want to find a particular y of x, which we can call y star of x, it is an unknown function that minimizes the functional j. So, if you recall, we call this thing a functional, which is a mapping from the function space to a real number space. We want to minimize that real number. J is now a functional, so it will be a real number, a scalar. We want to find this y star of x, that means that we have to search in the space in which this y of x is. Okay. And we said this minimization problem requires a necessary condition. For that we need to take equivalent of the derivative or gradient. Equivalent meaning if we consider where the unknowns are x1, x2, xn, then we took the gradient and said that the gradient should be equal to a 0 vector. Now, we take Gatu variation and set that equal to 0, that becomes the necessary condition. Okay. So, in order to take that Gatu variation, so what we defined in the last class TEAUX Gatu variation. If you recall, we had a limit definition and also we had normal calculus based definition. The latter is useful for us to do the calculation. So, what that meant was that we take the derivative of this functional j not defined in terms of y, but defined in terms of y plus epsilon h, and take derivative with respect to epsilon and substitute epsilon equal to 0. If we do that, then we get the variation of j with respect to y. Okay. To begin with, we will do this without considering the y double prime. Later we will consider, we will take only y and y prime. Okay. So, we have a functional j whose integrand depends on y and y prime. So, an example that we had taken last time was that this f can look like this, square root of 1 plus y prime square divided by, let us say, square root of y. Now, it is a function, this f is a function of y and y prime, that is what we have written. If we have something like that, based on this definition of Gatu variation, let us do for this problem. Okay. If you take this, we have d by d epsilon of j y plus epsilon h. So, we have to substitute into this integral x1 to x2 f. Now, wherever y is, we substitute y plus epsilon h. So, we say y plus epsilon h. Likewise, for y prime, which is here, we have to do derivative of y prime, the derivative of y prime epsilon h prime. Okay. In fact, I forgot here that I should write this thing as variation of j, I have to put y and h, because in the definition of Gattu variation this arbitrary function h, that is that h of x will be included. Okay. Today we will try to get rid of it, but until now it is there. So, variation of y including that h is how this is done. So, we have this now, and then we have to also put epsilon equal to 0. Now, we said that we can interchange the operations of differentiation and integration, okay, that we can do when these limits are not affected by this parameter. Okay. If we do this, then it will become integral x1 to x2. We take the differentiation inside d by d epsilon of f, which is a function of y plus epsilon h, and then y prime plus epsilon h prime dx. Okay. And then we will substitute epsilon equal to 0 when we are done with differentiation. Okay. So, now if you do this integral x1 to x2, we are taking derivative with respect to epsilon, but this function f depends on y plus epsilon h and then depends on y prime plus epsilon h prime. So, you have to use chain rule and write this as dou f by dou y plus epsilon h, because that is what is there in this function. Okay. And then we have to take derivative of this, that is derivative of that one with respect to epsilon, that gives us h here. Okay. And then we have to do for the second part, that will be dou f by dou y prime plus epsilon h prime, and then take derivative of this, which is with respect to epsilon, which is h prime. So, we get h prime and then dx. Now, in this we have to substitute epsilon equal to 0. When we do this, we get the integral x1 to x2 dou f by, if substitute epsilon equal to 0 here, okay, that will simply become dou f by dou y times h plus, again we look at this epsilon here, we substitute equal to 0, then we get dou f by dou y prime times h prime dx. Okay. So, now what we have here is what we call Gattu variation. Okay, that is the equivalent of the gradient as we discussed in the last lecture. Now, the necessary condition is that this Gattu variation should be equal to 0. So, we have an integral that says this integral should be equal to 0 is a necessary condition for any function y that we take. Where is y? Y is in this f, right, that you will get an integral and say the integral should be 0. Okay. Now, you see this, we still have this unknown function h and h prime. Actually, y is also unknown, but this h is an arbitrary function that you can choose whichever way you want, and we have that and also its derivative, and we have to somehow get rid of it by using an argument that this h is arbitrary. Okay. So, now if we proceed further, I will write what we had at the end of the last slide. So, what we have is this variation of y and h for the j that we considered. What we had is integral x1 to x2 dou f by dou y times h plus dou f by dou y prime times h prime dx this being equal to 0 is our necessary condition. This is our necessary condition, that being equal to 0. Now, we have to do a little bit of work to somehow get rid of this h and h prime. Okay. For that we will use a famous lemma, that is a basis for calculus of variations. When there is h, that lemma applies. When there is h prime also it applies, but it is convenient if we convert this h prime to h. Okay. That also gives us something more. So, what we do now is to use integration by parts to convert this into h and some boundary condition. Okay. So, this one to this term we apply integration by parts, apply integration by parts. It is just normal calculus, everybody would be familiar with integration by parts. So, we leave the first term as it is, integral x1 to x2, we leave the first term dou f by dou y h dx as it is. For the second one, we will take this as the first function, this as the second function, meaning normally what we write, the first function into integral of second function. So, h prime is there, integral of second function becomes h evaluated at the two end points, the boundary, and then minus, we are applying integration by parts to this second term, integral of minus integral of limits from x1 to x2, derivative of the first function, that is d by dx. So, now integration with respect to x, so you have to do that derivative with respect to x, d by dx of derivative of the first function into integral of the second function. H prime is the second function, now we write h. Now, we can collect the terms that are under the integral sign x1 to x2. We have dou f by dou y, there is a h here, this also h. So, I can take that minus d by dx of dou f by dou y prime together multiplied with this arbitrary function h. It is still arbitrary, is still with us, we have to somehow leave it somewhere, which we will do shortly, dx, and then we have the boundary term dou f by dou y prime h evaluated at x1 x2. Okay. That should be, so whatever we have done, that is equal to 0. So, this is equal to 0 and this is equal to 0, right. Now, we have an integral, we have this integral and we have this boundary term, right. These two, sum of these two should be equal to 0. There are different possibilities, each one of them can be 0 or the sum can be 0, but a sum can be 0 is little bit tricky, because this particular term is evaluated only at the two ends x1 x2, whereas this one, if you were to do integration, this is for the entire domain that you are doing, as opposed to the second term which is only for the end points. So, even if you construct a special function h and some y that you find, you probably can make it 0, but it will be applicable only for one particular h. If you want it to be applicable for any h, because so far let us recall that h is arbitrary, it is our choice. In the definition of Gattu variation, this h of x is arbitrary, we can take anything that we want. So, we want to retain that spirit. So, what we say is that this should be equal to 0 and this should be equal to 0. Okay. So, from here we write x1, x2 integral with limits x1 to x2 of this integral dou f by dou y minus d by dx of dou f by dou y prime multiplied by h dx is equal to 0, and we write something that is 0 dy dou f by dou y prime into h at the limits x1 x2 is equal to 0. That is what we say, because anything else that you do, you may be able to do for a particular h function h of x, but not for arbitrary h. Okay. So, we can write these two like this, all right. Now, let us take it further, this one and that one. So, I will write them again in a different color. So, we have x1 x2 dou f by dou y minus d by dx of dou f by dou y prime times h dx equal to 0, and we have dou f by dou y prime into h at the two limits x1 x2 equal to 0. That is what we had at the bottom of the last slide. Now, let us look at this. Okay. So, we want this to be true, that is this integral being 0, we want it to be true for any h, that is arbitrary, any function h, arbitrary, that means your choice or anybody's choice. Then there is something called a fundamental lemma in calculus of variations, which says that if we have, let us say, an integral such as this x1 x2, where I have something called phi, okay, some function times h dx equal to 0. If we say it is equal to 0 for any arbitrary h of x, okay, let us say we have something like this. What the fundamental lemma says is that this statement that f h for any h, if integral is 0, then it says that f must be identically 0 over the entire domain x1 to x2. So, this will be over your domain x1 to x2, it should be equal to 0 everywhere. Okay. So, for this is a phi which is a function of x when you do it, or this integrand part of it. So, for x that belongs to this interval anywhere, it should be, or everywhere it should be equal to 0. You have to think about this. This is called the fundamental lemma of calculus of variations. Fundamental lemma. So, lemma is a thing that is not good enough to be called a theorem. Okay. In fact, if you think about this, it is even intuitively obvious why it should be the case, because you have a function phi, you are multiplying by another function h, and you are calling that h to be an arbitrary function, and if it has to be 0, you better have phi equal to 0 everywhere. Otherwise, you construct an f for a given h, somebody will come and change the h because h is arbitrary, then this integral will not be 0. Okay. In fact, the proof of this also works by contradiction. Okay. That proof is not so important for us because this can be intuitively understood. So, this is fundamental lemma of calculus of variations, and that is what we will use now over here. Okay. We will use that over there, because what is our phi? Our phi now is this portion. Okay. That is our phi. For any arbitrary h, this integral phi h equal to 0 is satisfied only if this phi is equal to 0 everywhere. So, we write, okay, from here and our fundamental lemma together, we can write our equation. So, we write dou f by dou y minus d by dx of dou f by dou y prime equal to 0 for this x that you have. You will get some expression there for any x belonging to this interval x1 x2, okay. But we should not forget the boundary condition. So, the other one that we have over here. So, dou f by dou y prime h x1 x2 equal to 0. It may be actually wiser to keep them as these brackets rather than square brackets, because this interior, this is the boundary, right. So, this is on the boundary of the domain, that is x1 x2, this is interior everywhere, okay. So, for a given f, this thing is actually a differential equation, that is what we will get. We will do an example, but what we have here is a differential equation and the boundary conditions. For any differential equation, whether it is initial value problem or boundary value problem, you need conditions at the ends. If it is a boundary value problem, you need boundary conditions. If it is initial value problem, you need initial conditions. Here it is a boundary value problem, as we call BVP, boundary value problem. So, here is a differential equation, okay, and here are the boundary conditions, and that is what calculus of variation gives. Again, if you recall, what we started out with is a problem statement was minimize with respect to y of x an integral j from the limits x1 to x2, where the integrand depended on y and y prime dx, and then we took the Gattu variation and said that that being equal to 0 is the necessary condition. So, we got the equation, okay. So, again let us remind ourselves that we took Gattu variation, which is written j, y and h equal to 0, and then we used what we called the fundamental lemma, of calculus of variations, okay. And in between we also added to this integration by parts, okay. I am just recalling or summarizing the derivation that we just did, integration by parts. All of that gave us, all of these things gave us what we call the differential equation, which is dou f by dou y minus d by dx of dou f by dou y prime equal to 0 in the interior, and the boundary condition dou f by dou y prime into this h x1 x2 equal to 0. The h disappeared from the differential equation, there is no h here, but here we have h, okay. That is okay, because what we say here as the boundary condition is that at x1 as well as x2, this product, that is product of dou f by dou y prime and h should be equal to 0. How do we take care of that? Let us say at x1 y is specified. Y is specified, we are not allowed to take variation there. After all, h is the variation, right. So, it is a little perturbation we take around y. If we recall our Gattu variation definition, which had j y plus epsilon h, okay. H is the function that defines the variation, right. So, if y is specified, we are not allowed to have h different from 0 there. 0 should be assigned to h at that point. that automatically satisfies this. Likewise, if x2, if it is y is specified, then h will be 0, right. If y is not specified, then we say dou f by dou y prime should be equal to 0 there. That is how we get the boundary condition, either y is specified, if y is not specified, something else should be equal to 0, that is what dou f by dou y prime. Okay. So, this leads to two kinds of boundary conditions. First is the differential equation, okay, that is important, and using this differential equation we can find, okay, this enables us to calculate the solution function y star x. Okay. For that we also need the boundary conditions. We get two kinds of boundary conditions here. Okay. One is h equal to 0, other is dou f by dou y prime is equal to 0. H equal to 0, as we just discussed, it is when y is specified, y is specified. The problem specifies what y should be at the end, okay, in which case h should be equal to 0, the boundary condition is satisfied. If not, if y is not specified, y is not specified, okay, y, we will go to the next slide, y is not specified, then that should be equal to 0. So, let us go to next page and try to rewrite this. We have the differential equation, that is not a problem, dou f by dou y minus d by dx of dou f by dou y prime equal to 0, and the boundary condition has two possibilities, right, at both x1 and x2. Okay. So, one is that h equal to 0 when y is specified, dou f by dou y prime equal to 0 when y is not specified, okay, both at x1 as well as x2. Okay. And there is a name for it. Now, when y is specified, we call it essential boundary condition, or named after a mathematician, Dirichlet boundary condition. Dirichlet, I will write BC for boundary condition. So, BC stands for boundary condition. Okay. When y is not specified, we call that natural boundary condition, or named after a mathematician, Neumann boundary condition. So, calculus of variation not only gives once again the differential equation for the minimization problem, but also gives the boundary conditions, right, and these are called Euler Lagrange equations. The differential equation that we have written is called Euler Lagrange equations. Equations, I say that there could be multiple functions that you do not know, y1, y2, y3 and so forth. So, that is why we are saying Euler Lagrange equations in plural, otherwise just Euler Lagrange equations. Okay. So, if you want to try, let us take a particular y to begin with. Let us take 1 plus y prime square, okay, meaning that the integral that I am considering, the problem considering is minimize a j where let us say from x1 to x2 square root of 1 plus y prime square dx with respect to y of x. Then for this problem we can write the Euler Lagrange equation, the boundary condition, and try to find the solution, which we will do when we continue this lecture. Thank you.